All right, we're at the last section, 20.5, distribution of molecular speeds. So far, we've talked about the RMS speed. VRMS is equal to the square root of 3RT divided by M, the molar mass. Um, but the velocities inside a gas are very chaotic. Let me dismiss this so it doesn't interfere with um, the, the display. Uh, the velocities are some are going slow, some are going very fast, some are going very fast. But the RMS, the VRMS is given as 3RT, the square root of 3RT divided by M. And we have um, we defined a distribution function. Um, the uh, the NV NVE is the number density, and this quantity it's called a distribution function, and it's defined so that NVEDE is the number of molecules per unit volume with energy between E and E plus DE. In general, the number density is found from statistical mechanics to be NVE equals N0 E to the minus E KB divided by KBT. Um, now, this equation is known as the Boltzmann Distribution Law, and it's important in describing the statistical mechanics of a large number of molecules. Um, so basically, it states that the probability of finding the molecules in a particular energy state varies exponentially as the negative of the energy divided by the KBT. All the molecules would fall into the ground state if the thermal agitation of a temperature T did not excite the molecules to higher energy levels. Um, so this um, in 1860, James Clerk Maxwell. We'll study Maxwell much more later this year when we talk about Maxwell's equations. Uh, Maxwell derived an expression that describes the distribution of molecular speeds in a very definite manner. Uh, so it was controversial because no one um, could detect molecules uh, experimentally, but about 60 years later, the experiments were devised that confirmed Maxwell's prediction. And the we have what is known as the Maxwell-Boltzmann speed distribution function, shown here as NV, and from this we see that the here is the one we've been working with, VRMS. There is a V average, which is uh, right here, but this other is V most probable. The number of molecules having speeds ranging from V to V plus DE equals the area of the tan rectangle NVDV. So that's this here. Um, the So we can see that the VRMS is equal to the square root of the average V squared, and that's equal to 3 KBT divided by M0, and that's equal to 1.73 square root of KBT divided by M0. Now the V average is equal to square root of 8 KBT divided by pi M0, and that's equal to 1.6 square root of KBT M0. Now the most probable velocity is equal to the square root of 2 KBT divided by pi M0, and that's equal to 1.41 KBT M0. Now, let me go to this last slide. The total area under either curve is equal to n, the total number of molecules. In this case, n is equal to 10 to the fifth. Note that VRMS is greater than V average, is equal to V most probable. So the velocity the RMS velocity is greater than the average velocity is greater than the most probable velocity. Now I've taken the time in Mathematica to let me see if I can find it. Where's my Mathematica? Oh, I went through all that trouble. Now I can't find it. Oh, there it is. Hopefully you can see this, and there's there it is at 300, and you can see it's so it's saying there's about 200 molecules with this velocity, right, somewhere around 450. And we can see as we vary the temperature, I mean, if I go lower, it's starting at about 0 degrees C, which is 273, it goes over 200. But as we slide it, you can see it flattens out as it does in the textbook image that I just showed you. And where is it? I think they had it at 900. Let's just enter 900. And there it is. And we can enter 300 and you'll see it jump. But you can see the smooth transition as I slide the manipulate slider forward. As the temperature increases, the distribution gets more broad. And that is in keeping with our last slide here. There's T equals 300 Kelvin. And here's T equals 900 Kelvin, and you can see how the distribution broadens. Just wanted to demonstrate that with a little Mathematica plot. Okay, and I think that that ends the chapter.